In this video we're going to see how we can use the CORDIC algorithm in order to convert our coordinate systems from polar to rectangular and also rectangular to polar. So we will start off with polar to rectangular. Now this is just an extension of what we did in the previous video. In fact, the algorithm is just the same. We're just reinterpreting the outputs. So let's have a look at it in the graphical calculator. So what we have here is exactly the same simulation that we used in order to generate the sine, the cosine and the tangent functions. We have the initialization where we have x0 is equal to 0.607, and that's the x coordinate of this point here. And we have our y0, which is a value of 0. And we have the angle which we are given and we already know. So in this instance here, the angle is actually 30 degrees. So what we want to do in effect is reinterpret the inputs, and we'll also reinterpret the outputs. So as far as the input is concerned, what we're given is the angle theta. And also we're given this length here. But this length here is nothing other than a scaled version of the full length of the input, which is the value for our r. So in effect, this vector here has got a length r and it's got an angle theta. Now whenever we work through the algorithm, we're going to move this point to this point here. So I will quickly do that now. So our final output is the x and y coordinate of the point. And you can see that our approximation here is 0.8655, 0.5001, and the actual value is 0.866, 0.5, so we're very close. So now what we can do is reinterpret the outputs. We can see that the output for this simulation, again it is the xn is the cos theta, yn is the sine theta. But of course, in effect here we have the value of 1 in front of this cos theta and 1 in front of the sine theta. But the value 1, which is in front of both sine and cos, is just the length of the original vector. Now in this instance here, I've simplified it and I've made that vector of length 1. But of course the vector doesn't need to be of length 1, it can be of any length. So we could call that vector length r. So in effect the output we're going to get is going to be r cos theta and r sine theta. So in effect what we've done with this simulation is we've gone from the input values, which are our r and our theta, which are our polar coordinates, and the output is now going to be the value of our x and our y, which will be our rectangular coordinates. So we have performed a polar to rectangular coordinate transformation. So we used the CORDIC algorithm exactly the same way we used it when we generated the sine, the cosine and the tangent function. We just reinterpreted the input and the outputs, and you can see here I've added the value r here at the beginning and the r here before the sine theta, and previously this was just a value of 1, but now it's a value of r, which is just a scaled version. So finally, to summarise, what we've done is we've gone from the coordinate system, the polar coordinate system of r and theta, and we've gone to the rectangular coordinate system of x and y, and we've done it via the mathematical equations x equals r cos theta and y equals r sin theta. So let's go ahead and we'll now look at the rectangular to polar coordinate transformation.